In this video, I'm going to show you some problem-solving strategies when dealing with two-dimensional projectile motion. Let's look at this problem. A bocce ball is launched with an initial velocity of 15 meters per second from a cannon that's located on a platform that is 5 meters above the road. The cannon is at an angle of 20 degrees above the horizontal. Neglecting air resistance, let's calculate the horizontal distance the bocce ball will fly. As I taught you in the previous video, when we are looking at and dealing with two-dimensional projectile motion, it is critical that we break this into the X and Y directions and analyze those separately. We're going to be using the same strategies we employed in earlier videos when solving UAM problems in general. In other words, we're going to lay out our 5 variables and determine what we know, what we don't know, and what we're trying to find. Except this time we will do this for the Y direction, and then we will do it all over again for the X direction. Let's go ahead and get started. So our vertical displacement is negative 5 meters. Now signage is important here. Why is it negative? Because the ball will start here in the cannon and it will land down on the road, which is 5 meters down from its initial vertical position. Therefore, our change in vertical position is going to be 5 meters down, or negative 5 meters. Time. We know nothing about time. What about its initial vertical velocity? Well, as you learned in the previous video, we can use trigonometry to resolve the resultant vector into X and Y components. Let's take a look at that. Above my head here, you can see the cannon. Now let me show you the right-angled triangle so you can go ahead and understand the trigonometry involved here. We have our hypotenuse. Our hypotenuse is the 15 meters per second. That's the launch velocity. Then we can look at both the X and the Y components, and using trigonometry, it becomes evident that if we're solving for this opposite side here, which is V naught in the Y direction, we would use the sine function and rearrange it to get V sine of 20. Again, V would be the 15 meters per second, or the hypotenuse of the right-angled triangle. What about our final velocity vertical? We don't know. What about the acceleration due to gravity, which is the acceleration in the vertical direction, so little g? We know that because in projectile motion, these objects are under the sole influence of the force of gravity and are therefore accelerating at negative 10 meters per second per second. Okay, now let's look at what we know in the horizontal or X direction. See how this is different? We must lay these out separately. Our change in horizontal position, well, you know what? That's what this problem's asking for. It says calculate the horizontal distance the ball will fly. So that's what we're trying to find. Time. We don't know anything about time. However, from the previous video, we do know that that's a commonality between the vertical and the horizontal components. Whatever time is, it's the same for both. And we also know we must analyze the vertical to find time. Next, our horizontal initial launch velocity. Okay, well that would be the hypotenuse above my head multiplied by cosine of 20. Why cosine? Well, that's our adjacent side of the right-angled triangle. That's our initial horizontal velocity. Final horizontal velocity. In case you missed the last video, that never changes, and I went through that repeatedly. So our V final X is our V naught X. It doesn't change, therefore that is V multiplied by the cosine of 20. Of course, you know the acceleration horizontal is 0 meters per second, and I also showed you this in the previous video. If I take this UAM and I acknowledge and understand that there's no acceleration, no change in velocity over time horizontally, then this entire piece here goes away, and we're left with the only equation you will use in the horizontal, which is on the screen. The change in horizontal position equals v naught x times t, where v naught x is constant and will be referred to as the velocity in the x direction. Now, let's go ahead and continue to try to solve this problem. So, we need to find time. So you've been taught that if you have 3 out of 5, you can solve it. And that's still true. So using this UAM for the vertical component, we can find time. And don't we need time to solve for the horizontal distance? Yeah, we do. So let's go ahead and look at this. And I want you to acknowledge that you would need to use the quadratic formula when solving for time with this problem. Guys, we don't have time for all that. You don't have time to use this quadratic formula when you're looking at minimal time for FRQs and MCQs. When you encounter this, don't use the quadratic formula. There's an easier way to solve this. Instead, let's solve for the final velocity in the vertical and then solve for time. That way we avoid the quadratic formula altogether. And this will always work out for you. Now, let's look at our UAM that are left. This UAM includes time. Not going to work. This UAM, we know that one's not going to work. This UAM, it also includes time, which leaves us with one more, which is the only UAM equation that does not include time. That's the one we want to choose to solve for the final velocity in the vertical direction. So now let's go ahead and pop in our variables. 15 meters per second, sine of 20 is 5.1 meters per second. Remember, 15 meters per second is the initial launch velocity, or the hypotenuse, when we resolved into x and y components. So now we can go ahead and plug in these values. Please pay attention to your signage. We can rearrange this. Solving, taking the square root, we get that our final velocity is 11.2 meters per second. Now, because it's under the radical, you need to be smarter than your calculator. You need to say, I know that the direction of this bocce ball is down, and down is negative. So when you solve this problem and you take the square root, you will get 11.2, and that is going to be a negative direction for down. So I'm going to put that in for V final in the Y. Now that we know that, we can continue on and find time. So avoiding that quadratic formula, we solve for V final in the Y, which enables us to use any UAM of our choice to go ahead and solve for time. I've chosen the one you see on the screen. So putting in our values, including signage, we get the following expression. Again, I'm accentuating the importance of the signage here in this equation. Rearranging this and solving for time, we get that time is equal to 1.6 seconds. So now we know time. Notice now we know time for both the x and the y, because that is a commonality between the two. Solving for V naught x, 15 cosine of 20 degrees is 14.1 meters per second. Now we can solve for the horizontal distance the bocce ball flies, which is the purpose of this problem. That's what we're trying to find. And we use this very simple equation that is valid for the horizontal direction only. The hard part was finding time. We hit a quadratic, we backed out, we solved for V final, then we used V final to solve for time. Now it's easy. 14.1 meters per second multiplied by 23 or multiplied by 1.6 seconds gives us a change in horizontal position. This bocce ball should, we hope, fly 23 meters horizontally, neglecting air resistance. So now let's go ahead and see what's happening here in this PHET simulation. We have everything set up as described in the problem, including the mass of the bocce ball and the diameter of the bocce ball, and we're using 10 for the acceleration due to gravity. I have a target here, and let's go ahead and drag this bullseye to 23 and see if the physics is accurate here. Okay, now on the countdown, 5, 4, 3, 2, 1, launch. Here we go, fingers crossed. And yeah, it lands right on the target. So we can see we did it correctly. And we're getting a launch range of 23 meters horizontally. That's pretty cool. That feels good. Indeed, we've launched it with all of these variables and its distance in the horizontal 23 meters. So moving on, that was great. That was exciting. Now let's go ahead and look at an alternative solution. There's many ways to solve these problems. It depends on how your mind thinks. The reason I'm doing this is because there's so many little strategies that you can utilize to solve these problems that are referred to me as conceptual hurdles. Let's look at this real quick. Here, I've taken this and I've taken a screenshot when the ball is in this exact location. Maybe you see the symmetry here. I do. And remember, we can use symmetry of motion strategically to solve these problems. If we use symmetry here, we can break this into two parts. Part 1 is on the screen. If we use the UAM variables, we can say, what do we know? For part 1, the vertical change in position of the ball is started here, and we've stopped it here. We can do that. So it's 0. V naught in the y is still 5.1 meters per second from the trig. V final in the y. Oh, symmetry of motion. So it's equal in magnitude, opposite in direction. We can use that. If V naught y was 5.1 up, then V final y is 5.1 down. Very cool. Of course, acceleration is a little g. So now we can choose a UAM because we have 3 variables here. We can go ahead and plug and chug with these variables and get a time for part 1. Our time ends up being 1 second when we rearrange and solve that UAM. So now we know how long it took for this motion to be about 1 second. Part 2, well, this is where the object now continues falling 5 meters to the ground below. So our change in position in part 2 is -5 meters. Our final velocity from part 1 becomes our initial velocity for part 2. And our final velocity from part 1 was the -5.1. That actually is now our starting point for the second portion of this motion. We don't know the final velocity. We do know the acceleration is little g. So we can choose this UAM, which does not include time, and we can use it to solve for V final, just like we did in the first solution to this problem. So now that we know V final in the y direction is -11.2, which makes perfect sense, we can go ahead and use any UAM of choice to solve for time, paying attention to our signage, solving for time. We get time 2 to be 0.6 seconds. Now you can see if we take time from part 1 plus time from part 2, that's 1 second plus 6/10 of a second, we get 1.6 seconds. Does that sound familiar? It should. That's the same time we got using the other approach. Then we can use our equation for the horizontal, the only one you're going to use. We got 14.1, that was the 15 meters per second, cosine 20 degrees gave us that value. Now we have the time, and now we get the same exact distance of 23 meters using a very different approach to this problem. In this video, I've given you a number of strategies that will help you to solve two-dimensional projectile motion problems. I'll see you guys in class.